Hi. So from the video title you've probably already figured out that we're going to be writing an emulator which is going to emulate the Altair 8800. And essentially that computer is a very early computer that was released sort of in the 70s, and originally it was pretty much useless. You couldn't really do much with it, and it was only when you added things like a serial interface and a terminal and maybe a cassette adapter that the thing actually started to become useful. So we're not going to go right back to that early days. I'm not going to emulate the front panel or anything like that. The goal of this video will be to try and get it up and running Altair Basic, and then we'll try and enter one of the basic programs that we can get from the Altair 8800 clone site, and that will be the goal of this video. Just try and get a basic program running in the emulator. And from that we might branch out, we might try and start to get disk emulation working and trying to run things like CPM, but that will be probably in another video if I ever get round to it. So let's take a look at what we're up against. Okay, so this is a PDF I've found online, which I think has all the information we need to be able to emulate the processor that's inside the Altair, which is the Intel 8080. And essentially that's pretty much all an Altair is. It's just an Intel 8080 with, you know, a little bit of supporting hardware, you know, a bit of RAM, and there you go. Now I do have a little bit of knowledge about this because I grew up with the ZX Spectrum, so I know a little bit about the assembly language of the ZX Spectrum, and the Z80 that's used in that is very similar to the 8080. But I'm not really too up on opcode level programming. Yeah, I'm a little bit too young for that. But it doesn't look too complicated, so let's take a look and see what we've got. So we've got a bunch of 8-bit registers, and that's pretty much all it is. Just these registers here. So 8 8-bit registers and 2 16-bit. So we've got general purpose registers here, B, C, D, E, H and L. Then we have an A register called the accumulator, and this is the register that's used for pretty much everything. Yeah, addition, subtraction, bit shifting, all sorts of stuff. Any type of operation you do with data is generally done with the A register. Now the F register contains a bunch of flags, which we'll look at in a minute. SP, which is a stack pointer, that's used for shoving stuff on that you want to retrieve back later, or for shoving return addresses for call procedures onto the stack. Program counter, which is basically where it currently is in its current execution. And here we have the registers here, A through to L, and these are indexed. Okay, so if you look at the opcodes, you can see we have RRR here, R1, R2, and they're indexed in a 3-bit address. Okay, so we're going to utilize the way that works. And also we've got 16-bit registers. Now you might think, what 16-bit registers? Well, all these are basically just 2 8-bit registers glued together, yeah, which allow you to do 16-bit operations. So BC is basically a combination of B and C. Easy enough. And these are the flags. We have the carry flag. This is all explained here, but carry flag, if you perform an operation which would have resulted in a value greater than 255, so bigger than a byte can contain, the carry flag will get set. That bit is always 1. Parity, that just means whether you have an odd or even number of bits set in the byte you're looking at. That's not used. AC, auxiliary carry, sometimes called half carry or nibble carry, that's similar to carry, except it's basically set if the operation that you perform causes a carry from the first nibble to the second nibble. I'll explain that a bit later on. The Z flag is just 0. That's set if the operation resulted in a 0. And S is signed. which is set if the results bit 7 is set. The signed bit is generally used, well, it is used for signifying a negative number. But for the purposes of the emulator, all we need to do is just set that bit if bit 7 is set, and that's all. Okay, this explains how all the operations are formatted, and then a bit further down we've got the good stuff, all the operations that we need to emulate. Okay, so I've got Visual Studio 2019 started here, and I've just created a new project. So first thing I generally do is rename Form 1 to UI, and we'll rename the title of that window. Just call it Altair 8800. Okay. Now before we get into anything like this, let's start doing the processor. So let's create a new class. Okay, and we'll create the processor. So this is an i8080. So we'll create this class. There we go. Right, we'll make this an abstract class because we're going to utilize memory and ports and things in the subclass. So let's take a look at what we're up against. So as we've said, we've got 8-bit and 16-bit registers. Now the thing is, if I was writing this in C, and I have looked at a few emulators in C and C++, because there are hundreds of Altair emulators out there. It's a relatively easy system to emulate, I think. And you know, C and C++ are pretty loosely typed languages, and C# really isn't. So, and when you're emulating things at this level, a loosely typed language is very useful. Now I'm going to run into problems if I try using bools as ints, and I try and mix different types of variable types like ushorts, which are 16-bit values, and bytes, 8-bit values. So what I'm going to do, I'm going to treat everything as an int, just as a regular int, and then we're going to create properties to bit trim them and put them into the format that we actually want. So like we saw before, the registers are sort of arranged into indexes, so we're going to do it that way. We're going to use an index or an array for the registers. So let's first create an array for the registers. Okay, so like I said, we're using ints, and we'll use reg capitals for register, and we've basically got 8 of them. Okay, and this is going to be B, C, D, E, H, L. This one is not going to be used, and A. Okay, so that should be the order. Yep, and A is number 7. Yep. Okay, so now we need a way to access those registers. So we're going to do that via properties. So let's set up some properties. So do the A register first. So to get the A register, it's just going to be reg 7. But what we're going to do is bit trim it like that. Probably don't need to do that, but why not? Just let's just be on the safe side. And setting it, we're going to set reg 7 is going to equal the value from the set, and again bit trimmed like that. Okay. Okay, so we've got A, B, C, D, E, H, L. Okay. B, C, D, E, H, and L. Reg 0, okay, so that's 1, that's 2, that's 3, that's 4, that's 5, okay, and 6 not used. That's better. Okay, so there's all our 8-bit registers. Now our flags, which we'll set up here, we'll set them as bools here. So we've got the carry flag, okay, parity flag, alternate carry, we'll call that half carry, so half flag, 0 flag, and the sign flag. We're also going to have some other values, so we've got halt and we've got interrupt enable, and we'll deal with those later. Okay, so we need to access the flags, so we'll create properties for those as well. So private ints, so CF, this time in capitals, carry flag, and this will be get, and we want it to be 1 or 0 depending on what CF is, so that's going to be CF 1 0. And if we set it, if the integer we're setting it with is non-zero or if it's 0. So it's basically just going to be value is not equal to 0. So what we got, CF, PF, HF, ZF, SF. Okay, I'll just change these. So it's P, H, Z, and S. Okay, so we've also got a couple of 16-bit registers. And these are the stack pointer and the program counter. We've also got an interrupt vector as well, which we'll need. Okay, so let's deal with the combined 16-bit registers. So again, private, we'll do a property, and we'll do BC first. Okay, so to get BC, this is going to be B being the most significant byte and C being the least significant. So that's going to be the C register ORed with the B register, which is shifted to the left by 8 bits. Okay, that will deal with BC. And to set it, this is going to be 2 operations, so I can't use Pragma. C, which is the least significant, is going to be equal to the value, and we don't need to bit trim it because that will be done here. And B is going to be the value bit shifted to the right by 8 bits. Okay, oh, I've got an error. What have I got wrong here? Oh, don't need the... I said I didn't need Pragma. I still put the symbol in. Okay, so BC, what have we got? BC, DE, HL, and S. Well, we don't need SP yet. So we've got BC, DE, and HL. So it's E, D, and HL, L, H, L, and H. Right, we're also going to set up properties for the 3 registers here. So private int program counter. Now these are just straight 16-bit registers, so we don't need to combine anything, but we do need to bit trim them. So that's PC and 0xFFF. F. Okay, and to set, that's going to be PC equals value 0x and 0xFFF. Okay, so that's PC, and we want SP and IV. SP and IV. Okay, I think that's all the registers. Okay, so let's do some support code. We need ways to read and write memory. So let's create some functions for that. So public read mem. Okay, so we're going to pass the address we want to read into there. This is going to return an int. Obviously, everything's an int. Okay, and this is abstract. So this is going to be handled by whatever class implements this. And also what I'm going to do is put an underscore there, and I'm going to put a wrapper around this. So this can be private int read mem int address, and this is going to return read mem, the abstract version of it, addr, and then we bit trim. Okay, just to make sure we don't pass any invalid values back to the subclass. And we need write mem as well, so let's do those. Private, this is going to be void write mem int address, and then the value that we're passing in. And I'm going to need an abstract version of that as well. And no, private public. Okay, and this is just going to be write mem and addr bit trimmed, and the value, which is also bit trimmed, but that's only an 8-bit value. So there we go. So that's reading and writing to memory, the basics. Now we need to be able to read and write words, so 16-bit values. Okay, so private read word. Okay, so we pass address into that, returns an int. And this is just, so the first byte is the least significant, so read mem addr just read mem addr, and then we OR that with read mem addr +1, and that is going to be bit shifted to the left by 8 bits, and that should read a word. Okay, now write word. So private void write word, so int address, int value. Okay, so write mem, we can just go address value like that for the first one, because it will automatically get bit trimmed here anyway, so we can just pass it in like that. And write mem for ADDR +1, and this is going to be value bit shifted to the right 8 bits, and that should write a 16-bit value to memory. Okay, so instructions also fetch memory locations, like immediate instructions, so we need a way to read the next byte in the program counter. So that should be simple enough. So read next, actually we'll call that next byte. Yep, okay. And that should just be as simple as read mem program counter ++. And we also need next word, because sometimes they need to read 2 bytes. So private int next word, and this is read mem PC++, and then that's ORed with the next one, which is PC++ again, and that's bit shifted left by 8 bits. Okay. Alright, we're going to need functions to be able to push and pop things to the stack. So private push, and this is void. We're pushing a value onto the stack, so we should do that in one line. So that's just going to be, oh no, hang on, it's 2, because we always push 16-bit values. So, and this is in reverse, so the first byte that we push is going to be the most significant this time. So write mem, and we're writing to the stack pointer, and we're writing the most significant, but we need to take one away from the stack pointer before, not after. And then we're doing value bit shifted to the right 8, and then we can put the least significant byte in, which is just going to be val. Okay, and popping a value, so pop doesn't have any parameters, and we're returning, we can do this in one line actually, can't we? So we're returning read mem, and that's SP++, and that's ORed with read mem SP++ bit shifted left 8. Okay, stack pushing and popping sorted. Now in the opcodes we're going to have to access registers by their index. Int get reg, so get register, and this is the index of the register, and this should just be reg I, but we want to bit trim that. There we go. And to set the register, this is void, and we're setting it with a value, then that's reg I equals value bit trimmed. And also we can access the 16-bit pair registers and also the stack pointer by index. That occurs sometimes here where we've got PP. So let's set that up. So private int, we'll call this get reg pair, okay, int index, and this time we're going to need to switch on I. We've got no easy way of just accessing that. So case 0, that's BC, okay, so we can just return BC. Case 1 should be DE, okay, yeah, so return DE. Case 2 is HL, and case 3 is the stack pointer, and we'll use HL as the default just to stop that error, although that should never happen anyway. Okay, and set reg pair, so private void set reg pair, and we need the index of the register and the value. Okay, and again we'll switch on the index. So case 0, that's going to be BC equals value, break, whoop. Okay, case 1, that's DE equals value, break, case 2, HL equals that, break, and case 3, that's SP. No need for a default in there. Alright, these register index bits don't always occur at the start of the opcode, so we're going to need a way to retrieve that. So we'll call this mask. So private int mask, I'll call it mask 8. Okay, mask 8 for 8-bit register index mask, and we want the amount of bits, so that's the amount of bits we need to shift, and then we need the opcode that we're looking at. Okay, so we need to shift right by how many bits. So if we're looking at this one, we need to take the opcode, shift it right by 1, 2, 3, and then OR it with 7. So that's going to be op, shifted to the right by I bits, ANDed with, well, with 7. That gives us mask 8. Mask 16 for 16-bit registers, well, that's only 2 bits, so it's basically the same except we're ANDing it with 3. Okay. Undoubtedly we'll need to add more at some point, but I think that's enough supporting information to start doing the actual operations. So let's get on to that next time. I'm going to take a break now and just get a coffee, so I'll see you in a minute.